It's my great pleasure to introduce Josef from the University of Aachen. He is, I think, without a doubt, one of the great developers and scientists in the field of machine translation in terms of almost all areas of statistical methods. He has developed and extended not only the original Giza toolkit for alignment that essentially took the IBM models and made them part of the public domain, but he has since then done tremendous things with Giza++ as a, I think, quite substantial new extension, and we'll be talking today upon new maximum entropy techniques that further extend this paradigm. Josef works with Professor Franz and I at the University of Aachen, and I think together they are doing some of the most exciting work on the planet in this area. And we're very lucky to have him here. Thank you.
Thank you very much. I'm very happy to having get this invitation. Very happy to be here. So the topic of my talk is discriminative training and maximum entropy models for statistical machine translation. So to an overview, first I will describe in general the stochastic approach to statistical machine translation. I will review the standard paradigm, the source channel model, which is typically always used from all the people who make statistical machine translation. And as an alternative approach, I describe the direct maximum entropy model to statistical machine translation. And then I will shortly review the baseline model that I use, that is the alignment template approach to statistical machine translation that I developed during my PhD thesis. And then I will describe how to improve results for this system, which is normally seen in the framework of the source channel approach by discriminative training or by reinterpreting it somehow as direct maximum entropy translation model. I will show some results on the workmobile task and then conclusions. Okay, the stochastic approach to statistical machine translation. The standard approach that's typically used is, okay, so we want to minimize decision errors for translation. We translate, so as symbols I use always F for French words, E for English words. We want to translate from French to English. And so in order to minimize the decision errors for translation, minimize the sentence error rate, we maximize the posterior probability English given French. And according to Bayes' decision rule, we could equivalently maximize over probability for a language model for the English and the translation model in the wrong translation direction. So we have two independent probability distributions, a translation model, which links output string and input string, and we have a language model, which aims to guarantee the well-formedness of the output string. And, well, each of these can be modeled separately, hopefully. And then in the search process, we have to generate the target sentence with the highest probability. We have to hypothesize all target sentences and maximize the probability product of these two probabilities. And for training, we typically use some kind of maximum likelihood training to to train the model parameters. And this approach was suggested by an IBM research group beginning of the 90s. So that's the same as a picture. So we have source language text comes in, target language text comes out. We have one global search procedure where we have two knowledge sources, a language model and the translation model. But this approach has certain problems. So one problem is that this combination, so to multiply the probability of a language model with a translation model, is only known to be optimal if we have the true probability distributions. We don't have them, we only have very bad approximation to the true probability distributions. So we have a language model and we have a translation model. There might be a different way of combining these two to get better results. So probably we should use a different thing if we have then these two knowledge sources. In addition, there is no straightforward way to extend baseline statistical MT system. So in practice, it's very hard if we have an existing machine translation model to extend it somehow to integrate, for example, an additional knowledge source, to integrate WordNet into it or to integrate non-ontology. So it's very hard because these are very complicated models and changing these model things are very hard. And other thing, empirical observation that interestingly very often comparable translation quality can be obtained if you use this wrong decision rule where we simply multiply the language model with the translation model in a wrong translation direction. So simply doing this we very often obtain almost as good translation quality, for some cases even better translation quality than the normal source channel approach. But the problem from a theoretical viewpoint, how can we justify this? So if we are in the source channel approach and make this, then would simply be wrong from a theoretical viewpoint. Okay, so now I want to come to maximum entropy as an alternative viewpoint to statistical machine translation. I have now a few slides on maximum entropy, but probably I could skip them for this audience and directly, I assume that everybody is familiar with maximum entropy approach and ideas. So as alternative approach, we could use the maximum entropy framework. So we could define feature functions for which take as argument the English sentence and the French sentence, and these compute some value, some real number. And we have a lot of them, and then the maximum entropy framework says if you have these feature functions and we want to combine them optimally to optimally obtain a posterior probability, then we should combine these feature functions in this way, that we sum over the product of all the feature functions in one parameter for every feature function, and then we normalize this over all the possibilities. So this quantity here is then directly a posterior probability for the English sentence given the French sentence. So this is somehow a whole sentence maximum entropy model for statistical machine translation.
We don't need the denominator. I mean, the denominator is not a function of E. So
so it's not. That's true. It's not necessary. So the sum is not necessary, and the exponent is not necessary for the decision process in the end. But for training, then it's necessary. So I could omit them here, but for completeness, to have the formula here to describe this, I included this. So also this approach to statistical machine translation was suggested by an IBM research group, by the second generation statistical machine translation research group by Papinini et al. In a few papers. And as training criterion, so we simply use a maximum entropy training criterion. There would be possible to use different training criteria, but the standard approach would be to maximum class posterior probability for the training corpus. So we maximize this quantity on the sentence level for the training corpus. You can do this, for example, using the GIS algorithm or any other gradient descent thing. And the whole thing then would be somehow discriminative, because we directly model the posterior probability. We directly integrate all the different knowledge sources in order to model the posterior probability. We don't have two independent probability distributions that are modeled independently, but everything is integrated. And for me, at least, a very interesting thing has been to see that the source channel approach is basically a specialization of this approach. So we simply could use as feature function the logarithm of the language model and the logarithm of the translation model that we use then in our source channel approach, and using lambda equals to 1, it's exactly the same. So that's in the same thing. So we have the source language as target language check. We have one global search process, but instead of using a language model and translation model, we use a large number of different knowledge sources, which are then feature functions, together with the parameter for the corresponding feature function. And we could now have feature functions which model a language model thing, so which only depend on the English sentence. We could have feature functions which depend on both strings. And feature function could be anything. That's a nice thing here. It doesn't need to be a probability distribution that sums up to 1. Okay, so then typically we don't do neither the source channel approach nor the direct approach, directly modeling this probability, but we structure this using alignment models. So we introduce this hidden variable, the alignment, and develop then a probability distribution for French sentence alignment given the English sentence. And then in search, we perform the maximum approximation. So the maximum here has to be over the alignment also. I forgot this. So we perform the maximum approximation in search, not summing over all the different alignments, because it's simply computational too expensive. And in order to do this, to still have the direct maximum entropy approach as generalization of the source channel approach, what I do is simply integrating the alignment as variable for the feature function. And then...
Sorry, would you say it again? What is the approximation? I mean, the approximation is that you don't, that you take, it's a Viterbi approximation.
Yeah, Viterbi, maximum approximation, Viterbi approximation. So the maximization also has to be over A. I forgot this to write in the form.
There, right.
Yeah, it should be there. And also here, it should be there.
Okay.
And then doing this, so here I omitted then the exponential and the renormalization here. It's still a generalization of the source channel approach. Okay, so that is a different possibility to structure a statistical machine translation model, and I would suggest it's a better probability, and I will later on describe also why. So now to the baseline model that I use for statistical machine translation. That's the alignment template model. And then afterwards I will describe what feature functions I use for this alignment template model in order to view it as a direct maximum entropy model. Okay. So now the standard approach to statistical machine translation models is, as I said, single word based alignment models. So the translation probability is structured using the variable, the hidden alignment, and then the translation probability is typically decomposed into an alignment probability, alignment given the English sentence, and a single word based lexicon probability. So there's a dependence of one French word with one English word, and it's not typically it's not modeled that whole phrases could be aligned with whole phrases. And as models are then typically used, so the IBM models or the HMM alignment model, I recently developed a model which I call Model 6, which are all in this paradigm. And a typical refinement, because really making indirectly this way poses for many language pairs certain problems, is handling of word groups in the target language. So a typical refinement that often is heuristically introduced is that in the target language are formed word groups, thereby it's possible that a French word could be aligned to a whole sequence of target words. That's a typical refinement that's often done. But as a more systematic approach, So, but the problem then of the single word based translation models is that the word context is not taken into account. Word context has to be modeled by the language model. So that's the idea. And But that's very problematic, because the language model alone then has a task which it cannot solve. If you have here the sentence, the German sentence, wie wäre es morgen, and look at the words that are suggested by the single word based translation model, for every of these words, wie wäre es morgen, then these are the words. And now the task of the language model is to choose the correct word order, by also omitting words, by choosing the correct word for it. Also the possibility that one word might be chosen twice, or from one row it might be twice chosen a word. And as you see, if you go through this, a lot of different sentences could be formed by using these words, but many word sequences also make sense. So there could be a translation of some imaginary German sentence, but only one of them is the correct one. So and it's how about tomorrow? So how about and tomorrow? So it's somehow important to incorporate context dependency in the translation model, and this is done in the alignment template model. So the basic idea is of this model is I start with to train single word based alignment models, and for my whole training corpus I obtain alignments, an alignment matrix for every sentence pair, and then I extract from every sentence pair. So here I have one sentence pair. I extract all aligned phrase pairs. So I look into this matrix and I see that the first word is aligned with the first word, so that's one phrase pair, very trivial one. The first two words are aligned with the second two words, more complicated phrase pair, and so on. So I extract all substrings in the alignment matrix, which are aligned. So these are
alignment is based on a single word model.
Exactly. So I use then GSA++ in order to obtain this. I use typically then model 4 or this model 6 to get this matrix. And also this is then I train in one translation direction, the other one, and then combine these to get a generalized alignment matrix. So I try to obtain the best alignment matrix that I can find using single word based models. And then on top of this, then these phrases are extracted, and a statistical model is defined on the level of these phrases. So these are then examples of these phrases together with the alignment, therefore it's called alignment template. These are then all extracted, And the statistical translation model is described on this Lyman template. So the details of this model I omit now. This is the model in a generative, from a generative viewpoint. So I have the English words. And these words are then grouped together into phrases. So one word could be one phrase, or two words could be one phrase. Always consecutive words are grouped into phrases. Then these phrases could be reordered. There's a reordering step. And then for these phrases is chosen one of these alignment templates to translate it. So this is done here. Then I choose for an alignment template, here denoted as Z. And then having the alignment template, it's decided for the French words.
And how many go 4 grams I saw? I mean, is that the
it's up to, typically it's up to 7. So for Workmobile I use 7, for Chinese English I use only 4 because we only have 2 GB machines. It's a question of memory then in the end. But for other tasks I go up to 30 words, which are very small tasks. It depends. Typically then after 6 or 7 there is no real improvement.
So just to understand what you're doing, so you have this matrix where you put in, like, the 1 or whatever, you mark the positions which are aligned.
Yeah.
And now the way you presented it, this could well be just a visual task, right? I give you, if I have 10,000 sentences in my training, I would have 10,000 of these. And then I have to find out recurring patterns of these dots.
Well, I don't find recurring patterns. I simply take all the patterns that are there. I take everything.
So in this, for example, you take all 1 length strings, all 2 length strings, all 3 length strings. Absolutely everything.
Everything. Even taking the singletons. And they also had to improve them the results. So it's important it's good to take everything.
This is reminiscent of Bart's approach to parsing, right?
Yeah. So this data-oriented parsing idea, yes. Simply taking everything, and then having a good model to combine this, or to take into account that probably things that are seen only once have a larger chance of being wrong. So this has to be then taken into account in the model, how these are used.
But the template now is not lexical anymore, it's just a pattern of these.
Yes, it is.
It is lexical.
It's lexical. So, but the templates are then not stored on the level of single words, of the words itself, but on the level of word classes. So I can also do this on the word level, but in order to generalize, so therefore it's possible, for example, if I have a template that says on Wednesday, let's meet on Wednesday, then if in the word classes include then the weekdays in one class, then this pattern can also be applied for let's meet on Thursday, Friday, and so on. So these are stored then not on the level of words but on word classes, but are lexicalized from that for word classes. Okay, so that's a model from a generative viewpoint, a little bit simplified, but in the end, what comes out is then that if I write down in the search criterion, I have 4 component models. I have the language model. I have an alignment model, so the reordering of these phrases that I find. I have the model to choose the corresponding alignment template. And I have the model for choosing the word sequence given the alignment template in the source language words. So these are the 4 component models. Language model, first order alignment model on the phrase level, apply an alignment template and use an alignment template. That's in the end what has to be maximized in the search of the alignment templates, and these models then have to be trained somehow. Some of these probabilities are trained using a simple relative frequency, others are directly come out of GISA and so on. So there's a quite complicated, or a lot of things enter then in training, but I want to omit all this. Yes?
So how do you choose how many phrases get translated to how many phrases? Is that also has to be maximized?
In principle, there has to be a model for this, but so in the end, it's deficient. So there is no model that says which words have to be grouped together to phrases that comes out from which phrases really do exist. So there's also no model that decides how many phrases are there. Okay, so then what I could do, simply by doing, I probably it's hard to justify, but I can do this. I simply can use the same thing in the translation model in the wrong translation direction. I multiply the language model with the translation model in the wrong translation direction, and practically this allows in a much easier integration of the language model and the translation model. The reason for this is rather tricky would need to look into the model in more detail, but the nice thing then is that the translation model more or less decomposes over the English words. I have a probability for the first English word, for the second, for the third, and so on. And for the language model, as I use a trigram language model or n-gram language model, basically then it's the same, and I could integrate this very easily. Having it in the other direction, then it's much more complicated, and therefore the search for this, in this case, is much more efficient. And the nice thing is, if I do it this way, very often I have comparable results as doing it the correct way. So yeah, that's a simple fact. Okay, so now I can only shortly want to present some of the results that are obtained with this approach. So very often we observe that this approach gives systematic better results, or I think we had no case where it was the other way around, than single word based translation models, for example model 4. And so the system has been part of various evaluations. So for example the Workmobile evaluation, which was German-English speech translation, where then it was internally compared this with model 4, but externally it was compared to various other machine translation systems, so a classical transfer-based system, dialogue act-based translation, example-based translation, and the alignment template, the statistical approach. And the error rate here of the statistical approach was dramatically less than that of the other competing translation approaches. And then recently there had been this, in the CHILDS project, the Chinese English text translation, and there had been dry run evaluations, so not the formal evaluations, dry run evaluations in December. And there also, I don't compare it with the other competing systems because it was only dry run, but there have been also commercial systems as part of this evaluation, 6 different commercial systems, where LDC said it was basically what's available and affordable. And they obtained a NIST score between, so NIST score means somehow a precision on the trigram that's there with respect to various reference translation, and it said that it correlates well with subjective quality, and higher scores are here better. So these are error rates, so lower scores are better, here higher scores are better. And the commercial systems had between 8% NIST score to 16.4% NIST score, and the alignment template approach much larger error rate, NIST score.
So the error rate there is what error rate?
This error rate is subjective evaluation. So really there had been about 9,000 sentences subjectively evaluated by a large number of people, saying if they are correctly translated, understandable translated or not. So there it was not important to have a fluent or nice looking translation, but it was important that the translation is understandable. And using that evaluation criterion, then the alignment template.
So these are humans who judge it, first of all?
Yeah, yeah.
And the example based, that's the Japanese approach, is it?
Well, it's mainly the input sentence is there are found named entities, so dates or names or things like that, or places, and then from the resulting generalized sentence, the nearest match in the database is found. So I think they have about 20,000 sentences on the whole sentence level. It's not taking.
This exact, I mean, don't the Japanese, is there a group in Japan which calls its translation as an example based?
Yeah, I think there is a whole school in Japan that
yes. And you don't have it compared to the normal IBM model, whatever, 5 result. Right?
Yeah, yeah. So in this evaluation was not done by us. So this was done by a different group. And
so we don't know what the standard, what the quote best IBM 1993 result would.
No, we don't know. So we have made evaluations then internally on different test corpora, using our evaluation criteria, comparing it with model 4. And there it outperformed the other system. It's better, so the alignment template there were better than is better than model 4, but the gap is not so large as it seems to be here between the statistical approach and the other approaches. So the gap is smaller. And well, there have been additional evaluations in various other projects of this system, and typically it seems to perform quite good. And now I want to present something to improve on these results. Yeah. So the next section now is I entitled it Discriminative Training for the Alignment Template Approach. Equivalent title probably would be that the alignment template approach is reinterpreted as a whole sentence maximum entropy model, as I presented it in the beginning, or probably as then this IBM group would call it direct translation model for statistical machine translation, using then the alignment templates concept.
You haven't done any maximum entropy yet, right?
Yes, yet nothing. So it was simply using the translation model in the wrong translation direction. So that's in the baseline system. Okay, so what we could do in order to improve the baseline system is simply to introduce model scaling factors. So in the beginning I had comparing then the source channel approach with a maximum entropy approach. I said one is a specialization of the others, using as model scaling factors always lambda 1 equals lambda 2 equals 1. And now we could introduce model scaling factors, but not only for the language model and the translation model, but for all component models of the alignment templates. So for the language model, for the alignment model, and for the other models. So we have 4 model scaling factors, and we could try to make a discriminative training for these. So to directly optimize the posterior probability using these model scaling factors, and this means from the viewpoint of direct maximum entropy models that we have 4 feature functions, namely one feature function, the language model, the alignment model, and these other models. And here the feature functions depend on the hidden variables that are used in the alignment template approach. So this is then here omitted. And so it depends on the viewpoint which you prefer, if you make discriminative training for these lambdas, or if you say I have a direct maximum entropy model and use these 4 feature functions. So basically both are identical. But what I think is a better viewpoint is to say I have a direct maximum entropy translation model, because from this viewpoint these lambdas are introduced naturally. If I introduce the lambdas in the other model, like in speech recognition, introducing the language model scaling factor, it doesn't come out from theory, it's simply empirically done because it helps improve results. But if I interpret the whole thing as maximum entropy model and say I have feature functions, then it's natural to have these lambdas, which always help to improve results. And okay, so I skipped one formula, one slide. But for the direct maximum entropy approach, then I could introduce numerous other additional features, which then not necessarily have to be probability distributions, and can handle with various problems that my specific statistical machine translation system has. So which additional features are promising? So all the features which deal with specific problems that my statistical machine translation system then has. So as additional feature, I could, for example, use a number of produced words. So introducing some kind of word penalty, because I often observe that directly using my system, then the number, it produces too few words. So using also the model scaling factor always 1, the sentences are on average shorter than the reference translation, and that's bad. So I could say to the model, look at the length of the sentence by introducing this feature, and then it tries to make, at least on average, the length comparable. So that's a very simple feature. Additional features then would be simple additional language models. For example, I could use a Charniak parser, compute a probability for every sentence, and use the probability of this sentence as additional feature. And I simply can add language models. I don't have to think about that these then should be normalized or things like that, which makes things only complicated and not better. And for example, additional features so here I will use also an additional language model later on in the experiments, which is a class-based language model with a 5-gram history, so with a longer history, but on the level of word classes. Then as additional feature, I could use a manual lexicon, which simply says of my sentence pair that I'm currently looking on, how many words, how many co-occurrences in this sentence pair also occurs in a manual lexicon. In an additional dictionary that I have.
Also occurs in what?
In an additional dictionary. So if I have a standard dictionary downloaded from the web, which is non-statistical, I simply could say how many of the entries that are really in this sentence pair. And if there are very many, if there are more entries, then probably the sentence is better than if there are less entries.
And what do you do with phrases?
Well, also that if a dictionary entry is a phrase, then if this phrase is there and the corresponding translation phrase is in the other sentence.
No, but I mean, if there is a phrase which has individual words in the phrase that come from the dictionary, but the phrase itself is not in the dictionary, then that simply doesn't count.
Yeah, no.
So these features are a function of the alignment as well?
No, it doesn't take into account the alignment. It simply, even if the words are not aligned, but the corresponding words occur in the lexicon, then it's counted. And it comes out in the end that this feature doesn't improve results. So but I could use it. So using this dictionary that I use and this task that I use, this feature doesn't improve results. But it doesn't make results worse. So that's also a nice thing that typically then I could use features and typically they don't make results worse if I don't have overfitting problems. And in the end I only have up to 7 parameters, so overfitting is not a real problem. But I could use anything. I could use an additional translation model. I could use a model 4 or a syntax-based translation model if somebody develops one that gives good results. I could use it in addition to it. And I don't have to worry about how to integrate these different models and to worry about that everything should sum up to 1. Or a lot of different possibilities are there. So really this viewpoint from that statistical machine translation should directly maximize the posterior probability, and the maximum entropy viewpoint is a more general one, and I think a better one, because it allows for much more things. So now to the practical problems, how this can be implemented. So in principle, the training of these feature weights, because for every feature that we have 1 parameter, and this has to be trained, could be used, for example, the GIS algorithm, that is what I use, or any other training algorithm that's out there for this problem. There I implemented a toolkit, Jasmine toolkit, which does this. But in training, in principle, we have to renormalize these probabilities to obtain posterior probabilities, which are really necessary in training. In search, they are not necessary, but in training, they are. We have to renormalize over all possible English sentences. And that's somehow a problem because there are quite a lot of them. And in order to do this, I sample the space of all possible sentences using n-best lists. And well, n-best list might be too small. So that's, probably they're always too small, but they might be really too small that they make results worse. So I use
How do you get the n-best list?
I make various searches and extract
with some other model.
With the alignment template model, using my normal search algorithms that I have for the alignment templates, and make various searches using different model parameters. So varying these parameters that I have here, and then always extract the 20 best that remain in the end of the pruning. Yeah, at the end of the search.
But the model, you use a model which is not a maximum entropy model.
Yeah.
To do the n-best list.
Yeah, but I start with lambda values of 1.
Yes.
So and then that's a.
And so you keep iterating.
Yes, exactly. So that is what I do next. So I start with my normal model without any additional feature, perform the search, compute an n-best list, and then use this n-best list to optimize the parameters. Then I go back, make a search using these parameters. Extend my n-best list. I don't use this new n-best list, but extend the original one, and then optimize the parameters using this larger n-best list. And then I continue to do this, and it's guaranteed to converge, because in the end, theoretically, I would have all the sentences that are there. Finally, I converge, and then use the finally resulting parameters as result. Yes?
So I'm trying to understand the extension of n-best lists.
Yeah.
Is the only reason that when you extend the n-best list, is it just using the non-maximum entropy model, but with its newly adjusted parameters? Or do you do something else to add new candidates?
Sorry. Well, basically, the model in the beginning already is somehow a maximum entropy, or I use the same search algorithm for if it's a maximum entropy model or if it's not a maximum entropy model. It's exactly the same search algorithm. The only difference is that I weight the different component models by scaling factor. So if I'm in the logarithmic domain, I simply multiply my scores with the model scaling factor.
Okay,
in the beginning, I use lambda equal to 1.
Yes, no, I understand that lambda equal 1 is just a special case, but I had thought until about 10 seconds ago that you were using a different search algorithm for the lambda equals 1 case, which was simpler. I don't know what your search algorithm is.
I use always the same search algorithm. The only problem is with complicated features. So if I have features which cannot be easily integrated in my dynamic programming search.
Yes.
So for example, this lexicon feature.
Yes.
So this is really a feature that cannot be, at least I don't know a way to simply integrate this into the dynamic programming search. For this type of features, I do in the end rescoring of n-best lists.
So you've got a model without the features and a model with the features. You generate an n-best list without those difficult features.
Yeah,
and then you rescore by adding those difficult features in.
But
now, when you extend the end, yeah, that's right.
So far I use only one of these complicated features, namely this manual lexicon feature. And for all the other features, so for word penalty or additional language models, I can use directly my search algorithm because these are already there as component models of my search algorithm, and they easily can be integrated into this dynamic programming search.
Can you use length of the sentence in the dynamic programming?
Yeah, for every word that I produce, I add or subtract a score.
I see. So you have another factor of n in the runtime.
I have another?
In the runtime, then you must have another factor of n. Because
already in my original search algorithm, so in my search algorithm that could be solved differently, yes, I distinguish hypotheses according to the sentence length.
Yeah.
So that's was already in my original search algorithm. So you are right. It might be the case that then this must be part of the hypothesis, and so it introduced additional search efforts. But that was already also in my original search algorithm.
Okay, and when you iteratively extend the n-best lists, the reason that the n-best lists change is that the parameters to the when we talk about the simple model that you can search with dynamic programming, the parameters to that model change.
Yeah. So it might be the case if I have an n-best list, 100 bests, I optimize parameters on these, and I make afterwards search using these parameters, that I'm a completely different search space, and that these parameters which improve on this n-best lists are effectively worse in this other area. So what I do is I combine in this search space with this one and make it an addition, and then I might reach a different area. And so I will hopefully in the end I will cover enough of these areas in a reasonable amount of time. So typically then on these experiments which I do, after 7 iterations it almost doesn't change. So probably for larger sentences this might be a problem. The sentence length there is on average about 20 words. So and what comes out are 700 or 600 best lists. So in that order of magnitude, then the best lists come out. Okay, and then what already then is question came out, how to perform in search using these model parameters. So the model scaling factors, the word penalty, additional left to right language models are very easy to integrate in the DP search. So these are then part of the DP search algorithm. And for complex features, it's I do rescoring of n-best lists and obviously might make search errors using these more complex features. And that might be also an interesting thing to think about, which features can be easily integrated into a DP search and which can't. So, and then to come up with interesting features which can be efficiently integrated into DP search. Okay, and then there's an additional statistical machine translation specific problem that, for example, doesn't exist, at least in that sense, in speech recognition, if discriminative training is done there, that there is more than one reference translation. There are more than one correct translations of a sentence, and also in my corpus, I might have in the test corpus or in the development corpus where I optimize these parameters, there might be more reference translation. I might want to make use of them. Not only to use one, but to use many of them. And in addition, none of these reference translation, it might be the case that none of these could be hypothesized in search, and that's a problem if I want to try to push my model in that direction, because it in principle has a probability of 0. So that might be, for example, the case if in the reference translation there's a word that I've never seen in my training corpus, then I assign it probability 0. And also in search, typically in my dynamic programming search, there's some kind of observation pruning, where for every word that's in the source language, I only hypothesize up to 10 words in the target language. And so the vocabulary that I then in search, in my search space really look at is restricted. It's not the full vocabulary, but a restricted vocabulary. And so it might be the case that none of the reference translation, and in fact it occurs quite often, that none of the reference translation I really can hypothesize in search. And so as solution to this, what I do is...
Why is that an issue? Where is it come up?
Which, the second, or the first or the second? Or...
It's just the problem of making sure your search hypothesizes reference transcription. Where is that an issue?
What do you mean, where is it? My search algorithm as it is, in order to also to obtain efficiently results, makes this type of pruning, and therefore it doesn't hypothesize all the words. And in addition, it really might be a principal problem that if there's a word in the reference translation which is not in my vocabulary, I cannot hypothesize it. So that's
I don't understand. I mean, if we just give it some small probability, nothing is 0 probability. Why should anything have 0 probability here? I mean,
well, okay, but I want,
right, of some sort.
But I want that the model gives this sentence a very high probability, because that's my target. The reference translation, I want to push the model in order to give the reference translation a higher probability.
Yes.
But if the reference translation then has a 0 probability per definition, or a very small smooth probability, how can I push my model in that direction?
Can you point to this in the training criteria and say exactly where it shows up?
So here then. That's basically the probability, the posterior probability of an English sentence to a French sentence. And if the English sentence simply cannot be hypothesized by my model, then it gets probability, then I have to somehow assign the probability 0.
Let's see if I understand it. We start out with an aligned corpus, more or less.
Yeah.
With reference translations, and that's my training.
Yeah.
And from the training, I extract some kind of parameter values. I mean,
yep.
Templates, let's put it that way. My original templates will come from some aligned corpus.
Yeah. That's the original training corpus, but then these parameters are optimized on a development.
So now I have the template. I believe the templates won't change, right?
Yeah, they remain exactly
the only
the same.
thing that remains now is the lambda.
Exactly.
Alright, so I now use whatever I have and I create artificial hypotheses.
Yeah.
Meaning, by the model, they are not hypotheses that I see in some held out set.
Exactly.
And that's what gives me the n best.
Yeah.
I mean, so from every sentence I produce n best. From every French sentence in some corpus I produce n best.
Yeah.
This. By the way, the French sentence is from the training corpus. No. French test will be from some other French.
Additional development corpus.
From some other. So I will have it. All right. So then I start training for lambdas.
Yeah.
Okay, and I extract the features and do the whatever scaling.
But I need for doing the scaling, I need the corresponding feature values for the reference translations.
Just a second.
So that's important.
Pardon me. Is the issue that so you estimated this probability here? This comes from some performing probabilities. Were those estimated on some data set that's different from the data set that you're doing the lab?
Yeah.
Oh, okay.
Yeah.
Okay, I'm now lost again. I thought that we have with finality extracted the templates.
The templates are fixed.
Will not be done, and the only thing we're doing is evaluating lambdas.
Yeah.
And the way we evaluate lambdas is that we generate from the model as it stands an n best lists, and then we evaluate, then we have a guess at lambdas and we converge, let's say, with iterative scaling for new lambdas. Now that we have new lambdas, we go back and generate new n-best lists.
Yeah.
And we unite these n-best lists because you're afraid to go to the new n-best list because maybe we would go to some hole and we don't want to go down that hole.
Exactly.
So we keep going. So as we keep iterating, the sets of n-best lists keep growing.
Yeah.
Eventually you get sick of it and you stop.
Yeah.
And that's our n-best.
Yeah.
All right.
One other question. When you start off, you first produce a 100 best list and then you add another 100 to it.
Yeah.
Why don't you start off with the reference translation on top?
Well, I try to integrate also the reference translation by making a forced alignment to get the scores for the reference translation. But as I said, in my search algorithm, the reference translation might not come out from forced alignment.
No, that's okay, but just put it on top even before anybody else gets hypothesized. Right from the beginning. So you have
Just always included in the n-best list. You have a discriminative
before
model.
your first iteration, you have a 0 best list, and then it becomes 100, and then 200, and then 300.
Okay, that would be
a start with 1 and then go to 1.
Wouldn't I don't think that it wouldn't change a lot. So probably the number of iterations here then could be a little bit reduced because I'm already. But I also need something to compare with in discriminative training. So I need also bad competitors. So making this training only having the reference translation won't work. And also my reference translation, what I do then here is that I redefine the reference translation. That's an important thing then. I define its reference translation, then all the sentences that I have in the n-best list. So in the end I have an n-best list with 700 sentences. And the reference translations that I then use are those with a minimal number of word errors, or are the sentences of the n-best list with a minimal number of word errors with respect to the reference translations. And this is then the set of reference translations that I really use. So I don't try to obtain this ideal reference translation, which I cannot obtain by the limitation of my search algorithm. I try to get to something that I really can obtain in my n-best list, but something which is very similar to the perfect reference translation. So that's the thing that's here. And then my final criterion, maximum posterior probability criterion, simply changes as I sum here in addition over the number of, because I might have various reference translations for these two reasons, and I sum over all of these and divide them by the number of reference translations. So that's the final criterion that I use in training.
I got confused. So these reference translations are not generated by people?
No. They are those sentences which are in my, I only take as reference translation sentences which I have in my n-best list, so which I know I can produce and my search algorithm can produce. But I take from those the ones which are nearest to the true reference translation. So if it's really the case that I can produce the correct reference translation in my search algorithm, then this is chosen because there are 0 word errors with respect to the reference translation, because it's identical. Then I take it, but if it's not possible, then I take, well, the ones with 1 word error, with 2 word errors, depending on what is
the idea, for instance, that the translations will be more literal, the ones that you take than the reference, because the reference translation has all this stupid creativity by the translators that they always try to put in. And your best thing won't have that creativity. It will be, in fact, a straightforward translation.
Yeah, okay, so that might happen in addition. That was not my original motivation, but that might happen in addition. Yeah.
What was the original motivation? Why do this?
Because I need to have, I need to be able to push my model to something that the model really can generate. At least I don't know of a way in order to push it then in the near of this reference translation, which it principally cannot hypothesize in search.
So how
But maybe if you try
often
to-
do you not generate the reference translation?
Let me think. I think I've not done recent experiments in that direction, but it's in the order of 50%. It has been for different corpus, and so it really depends on the corpus. For very simple corpora, we have very simple corpus with a vocabulary of 500 words. So there I can produce 97-98%. But for this work mobile corpus, I think it was about 50%.
So 50% of the time the model is
So if
Well,
this
no,
is
not exactly.
But it's not on the invest list.
It's not on the invest list, so.
No, that's not what he said.
so
Out in left field.
it all so okay. Probably if I make a forced alignment, it will get a very very bad score, and it doesn't get 0 score, but a very very bad score. But then for me it's 0.
I see.
Oh, I
So there's some specific problems in this that you hope with this particular reference, and you hope to somehow find references that are real close, that have some higher probability of your model, and these are what will form will be used to supervise the training process.
Maybe the way to think of it is that you're giving up on ever being able to boost the reference translation high enough because it's so bad. So you'd rather get the things which you could generate.
What you're training right now isn't anything that drives the search for the index lists. And no matter how if you were trying to train something that could discriminate against, what you're training will never put the reference into the index list if it wasn't there from your earlier search state.
Yeah, that's what I'm saying.
So I'm if in the end I will use these parameters to translate new sentences, and my search algorithm will never be able probably to produce these great fancy translations that are in the reference, but it will produce hopefully sentences which are very near to that, because that's also then the evaluation criterion, to be near to the correct translation. And then I do the best what I can in order to within my possibilities, within the possibilities of the search algorithm. I do the best what I can. So probably if I would try to get to very badly scored reference translations that I have using fancy smoothing techniques, and so probably I could also give these some probability. But in the end, I would never hypothesize them in real search. And so probably I put then the model parameters, this lambda, in a direction which doesn't help me in the end. And I know these sentences I really can hypothesize, and my model is able to do this because they are in my investors.
So I'm trying to think of like what would be hard to find using your search that would be ranked very low. And things which come to mind are maybe missing words on either side, missing translations. The other thing would be sentences of very big difference in size. Do you think those are true, or what do you think the things that? What do you think? Can you characterize the reference translations that you're missing?
So one thing is the vocabulary itself. So the vocabulary is not in my target language vocabulary that I have in the model. The other is that the lexicon probabilities are incomplete, and in addition I prune them in search, but I hypothesize only 10 words per word. So these are the main reasons. And then also obviously probably this reordering is not hypothesized because it's over sentence boundaries and things like that.
You may be in a tight spot with
We're fine.
Okay.
Everything's in another room, but we still should.
Well, a number of students are in class too.
Yes, indeed, including Jason. So we have several meetings scheduled for this next few days, including one at 10 o'clock tomorrow and one at 10 o'clock Wednesday, in which Franz could continue to talk in the spirit of this dialogue. Now the question is, there are visitors here who will not be able to attend tomorrow morning at 10 as we had scheduled. Okay. I apologize for our Maryland visitors. Perhaps you would be willing in your visit to Maryland to actually start at slide 122 and continue on for their benefit.
So wait a minute, you're saying that this will continue?
This will continue exactly where he left off. Tomorrow morning starting at 10.
Not today in our conference room, for instance.
We could do it today. Tomorrow morning at 10. Okay. And then we'll have the discussion we had planned starting from this as a starting point. Perhaps the three of us can arrange appropriate visit time for Franz to Maryland. It will continue there as well.
What do you have yet?
How much more do you have?
How many slides come? I think in addition, not too many. Now comes the evaluation results and then conclusions. So about 7 slides.
So why couldn't we have these 7 slides?
Why don't you have the 7 slides? Those of you who have to leave, feel free to do so.
Some of us have to leave. We leave.
And we might actually review the 7 slides tomorrow as well.
Okay.
If you can stay,
I see. I have nothing more.
and also for the posterity, video recorded for the next 7 slides too. Okay.
So what are we doing now?
We will
Why are
have
these guys doing it?
They have the class.
I'm teaching.
Oh, you're teaching.
So if you have to leave, I'll do so rapidly, and then we will continue for the next few minutes on the next 7 slides.
Okay. So then comes the experiment that I did for this. So as evaluation criteria, as in statistical machine or machine translation, there is no standard evaluation criterion. I use many of them. So I use the word error rate, simply comparing with a reference translation the number of word errors. As in speech recognition, the multi-reference word error rate, where I use all the reference translations that I have, not only the initially given one. IBM recently suggested as evaluation criterion this blue score or bleu score, I don't know how it's pronounced, which is developed at IBM, and which is basically a weighted precision of n-grams in addition with a length penalty and some parameters optimized in order to make it good correlated to the subjective scoring. In addition, it uses subjective sentence error rate, so each translation is judged according to an error scale, according to a human, with an error scale of 0 to 10 points. And in addition, information item error rate, where the sentence is segmented into information items. So a sentence, let's meet tomorrow in Munich, is then one information item, let's meet, tomorrow is one, in Munich is one, and then the human evaluator says the information item is there or is not there. So these error rates are used. As corpus is used the Verbenwheel corpus with about 500,000 running words in German and English. So on this corpus then the alignment templates are trained, the language model is trained.
This is the Verbenwheel corpus, which has to do with meetings.
Exactly. So
And the German and the English are artificial. In other words, they are done for the purpose of this corpus. It's not some independent.
No, the corpus contains a lot of dialogues about making an appointment.
No, but they were done. But the translations were done in order that Verbenwheel work.
Yes, exactly.
It's not done so IBM would get applause. Hensal is done because the Canadians want to talk in their parliament. This is not the case here.
The translations were done on purpose for making
so
Verbenwheel running.
So, for instance, they will probably not have these flies so fancy.
Not so much, but the translators couldn't resist also here to introduce.
Couldn't resist even here.
But it's more literally translated
yes.
It would be.
It's more reasonable. Yes.
Yeah. And so the development corpus, on this corpus are then optimized these model parameters, includes a much smaller amount of sentences, words.
What's the vocabulary of this tag?
It's in German 8,000 words, English almost 5,000 words. So in addition there is a manual lexicon that I forgot to put here. So in the end the vocabulary is larger, so it's in German it's 10,000 and in English about 7,000 to cover, there's an official word list in Verbenwheel which the speech organizer can output, and so we translate all these words. And here the model scaling parameters are trained. So the corpus is quite small, but we only have at maximum 7 model parameters. So we have no overfitting problem. And then the tests are done on independent test corpus with 2,600 words. And for maximum entropy, the GIS algorithm was used using 10,000 training iterations, and in the end, a 600 best used. So here are the translation results that are obtained. In the beginning is shown the results for the non-standard decision rule. So for the translation model features are used from probability of English given French, not the normal source channel approach. And in the first line there is the old baseline. So this is the baseline which I originally had, which included some optimization as they are always done, going through model parameters, going through the language model scaling factor. There was also implemented some kind of word penalty, which was heuristically implemented. And so some of the things which are then afterwards are already in the old baseline, but parameter tuning. And so a lot of numbers. Let's look at the blue score and the subjective sentence error rate. So what here
blue score, the higher the better?
Yeah, that's important, yes. The higher the better. So all the others are error rates. I would suggest that IBM would have defined also an error rate while making accuracy. Then things get more complicated, but they define it as that and I use it as well.
George Dyer can change the
Now I think he also then has these scores which higher numbers are better.
Well, let's find everything.
A likes to things go down.
Okay, well, anyway.
So here the blue score was 50.7. The subjective sentence error is 31%. And if I use then as baseline simply what I described in the beginning, so these four models, language model, all the model scaling factors to 1, then I get much worse results, so 43%.
Baseline is
36.
single words also. Always.
No, always alignment templates.
Always got
and always the same alignment templates also. So and always the same language model. So this doesn't change.
I see.
And then if I train these parameters with maximum entropy, I obtain 5% improvement, so 43 to 48. Also the subjective sentence error rate goes down. If I use in addition the word penalty, I have an additional improvement here, 4%, 2%. If I use an additional class-based language model, additional 2%, and this manual lexicon doesn't improve. It slightly deteriorates the results, but basically these changes are noise, I would think. And yeah.
Do you think these errors are sort of correlated? Did you sort of guess that from your experiments?
Sorry?
So there are 5 types of errors. So are these error rates correlated?
More or less, yeah. Very often they are correlated. So word error rate probably is not so good, but these measures, multi-reference word error rate, blue score, or subjective sentence error rate, are very much correlated. The subjective sentence error rate often can fluctuate. So because sometimes one specific type of sentence is translated wrongly because one word is chosen wrongly, and then the humans say it's a wrong sentence, and the score goes from 1 to 0. And the other error rates, multi-reference word error rate or blue, are more smooth. But in the end, the important thing obviously is this subjective score. But very often in our experiments, these 3 error rates are very much correlated. So in order to optimize model parameters, it's possible to use blue or multi-reference word error rate, and in the end it helps to also to improve subjective sentence error rate. But it's important always to check if that's really the case.
What do you think about just plain word error rate?
Sorry?
What do you think about just plain word error rate?
Yeah, this has real problems. So it often is also correlated, but using only word error rate, for example, then the optimal is also to make shorter sentences. And so if I optimize the word penalty using the word error rate, I get a very, very different value from optimizing word penalty using subjective sentence error rate, and I get subjective very bad translation quality. So that.
Then I don't understand why. How is word error rate measured?
How is word error rate what
measured?
How is like in speech recognition? So I compare with the reference translation.
So why would it favor shorter?
Because I have a reordering problem. If I have a word at the wrong position in the sentence, this counts as 2 word errors. And then it's better not to produce this word at all, because this only causes 1 error. Yeah.
I would suggest if we could go on. I'm supposed to be in the same meeting that I just don't take meetings that seriously, but I should be in the same meeting Sanjeev went to. So if we could go through it,
okay,
and maybe have more debate afterwards, and I will be happy.
And tomorrow morning as well. And tomorrow at 10.
Yes, right. Just go.
Okay.
Go to the next.
So then the source channel approach, we could do the same for the source channel approach, having then the translation model in the other translation direction. Then we said the baseline gives better results than the baseline here. But then we could also optimize, introduce all these model parameters, and then in the end we are slightly better than this here. So here we have, at least in the subjective sentence error rate, we are slightly better, so 1% here. Here we are worse by 1%. So in the end we have more or less comparable translation quality, but as I said before, search for this model is much, much more efficient than search for this model. So here I can search for Workmobile a sentence in a second, more or less. And here it takes orders of magnitude more in order to make a search error-free search. And so therefore it's okay to use this. And the important thing is not, I think, source channel or not, but the important thing is that the translation model has good features. Namely, for example, taking into account whole phrases. And if the probabilities are normalized in that direction or that direction, is unimportant. Okay, so here the sentence error rate during the training of the GIS algorithm. Here we have GIS training algorithms 10,000. Here's the sentence error rate, and yeah, it goes down if you use only these 4 features. If you use in addition the word penalty, it goes further down using additional language model and so on. So this is that. On the development corpus this is, and that's then the same on the test corpus. So also here it goes down. We don't see significant overfitting. Yeah, so these are then the resulting model parameters that come out. So here for the 4 models, so the model scaling factors are normalized such that the sum of these first 4 sum up to 4. So in the end, the absolute value of these doesn't play a role, so I could multiply them with anything, and for the decision rule nothing changes. And the first 4 are also more or less comparable because probability distributions, the efficient one, but the probability distributions are combined. So we see that the alignment template model gets a much higher score, 2.33. The alignment model a very low score. Using in addition the word penalty, then all the parameters change because all the features are taken into account, gets a quite high value of 2.6. So this means for every word that is produced, the score, so logarithm of some kind of probability, is added of 2.6 or subtracted, I don't know. Then class-based language model, all the parameters change, and manual lexicon also gets a high feature weight, but obviously doesn't help a lot. And then, okay, training perplexity and error rate goes down if you use more features. So as summary, I presented this stochastic approach.
This is your last slide.
Then I will come to the outlook. So I make this very quickly. So the source channel approach is alternative to the direct maximum entropy model, which is, I think, a more general framework. So statistical machine translation probably in the paper shouldn't be described in the beginning using this source channel approach, but using this direct maximum entropy approach, which was originally suggested by Papignini. It's a more general framework, allows an easy refinement of existing machine translation system, allows modularization of development. Different people can independently work on different feature functions, and in the end everything could be combined. Allows easy integration of existing knowledge sources, so we could define some features that depend on WordNet or on some ontology. I presented the alignment template approach with a phrase-based statistical translation model, discriminative training for alignment templates, or probably it's better to say using the alignment templates as part of a direct maximum entropy model, and results on the workenwheel using show to improve results. So as outlook, obviously the important thing is which features. So we could now come up with a lot of ideas about features, so grammar-based language models, additional knowledge sources. A good idea probably is to combine different translation models, model for alignment and a syntax-based model. Also we could combine translation models in different translation directions. So for example, Dan Melamed is very often saying we need symmetric translation models. So simply we could take translation model English given French, French given English, and combine these together in order to get effectively symmetric translation models. Or if you want to introduce, for example, soft constraints, to say if you have a phrase in English and a phrase in French, then this phrase should be transferred contiguous. But introducing a hard constraint would make results worse. But using this approach, we have a possibility to introduce this type of soft constraints, that the model learns, okay, it's very often good to keep the phrases contiguous, and to introduce then this as feature function. All these things could also be done to improve alignment models, to improve alignment quality. So, for example, for Chinese English, it might be good to make features to inform the model about what Chinese words probably should be grouped together and should be aligned to one English word. So to make then alignment models and segmentation models as one model. So something that I also did is statistical multi-source translation, where I use more than one source language to produce a better target translation. So this works quite well. This could very easily be described in the framework of the source channel approach, but probably using this viewpoint significantly better results can be obtained, because then these model scaling factors could improve results. So then we would have model scaling factors for the different source languages, and probably one source language is better to translate into a specific target language than others. And this.
Did you talk about that?
No. So it's all. So I had a paper on that on the MT summit about that. So it's a quite nice approach, and it really seems to very easily improve results. And in that framework, probably the results could be even better. And obviously, the best and next thing then to do is to directly optimize the error rate. So, for example, to directly optimize the Bleu score, or to directly optimize the word error rate, or the word error rate that we think is appropriate for statistical machine translation. And then this is probably related to DMZ from Peter Bayerlein, who does this for speech recognition and for the word error rate. Okay, that's it. Thank you very much.